everyone. I will be presenting our paper on the complexity of recovering incidence matrices at this online ESA. My name is Ramanujan, and this is joint work with my co-authors Farah Fomin, Peter Golovach, and Pranavindu Mishra. So let me begin by sketching the general setting and try to say a little bit about why we are interested in this type of problem. Well, the kind of problems that we are interested in this work is what we call graph recovering problems. So just think of the setting as follows. Well, suppose that I give you a binary matrix, and I promise you that this matrix is obtained by taking the incidence matrix of some undirected graph and perturbing it slightly in some way. But then I could ask you, well, under this promise that the perturbation is small, can you efficiently recover the perturbed incidence matrix from the given matrix M? Right? So think of the perturbation as some kind of noise, and what you're trying to do is recover the original matrix from this noisy input. And a very natural related question then is, well, there need not be just one incidence matrix whose perturbation uh, puts me or brings me to M. Well, there could be multiple such incidence matrices. Uh, could I possibly identify them all? And how efficiently would I be able to do this? And of course, well, what are the appropriate notions of perturbation where such problems make sense? Now, let me say a little bit about one specific notion of perturbation and uh, where uh, this has been used and how it started us off on this journey in the first place. So, a very natural notion of perturbation is adding a small rank matrix to the incidence matrix. So here, whenever I say add, I'm talking about addition in GF2. And with this notion of perturbation, there is a very natural problem that can be formulated. This is a problem that we call min rank recovery. So you're given an n cross m binary matrix M, and you're also given an integer r. And the question is whether you can write M as the summation of two matrices L and S, where L is a low rank binary matrix. In this case, it is a matrix of rank at most R, and S is the incidence matrix of some undirected simple graph. So what was our starting point? Well, it was this work of Gillen and Kapadia, who studied perturbed graphic matroids, which are essentially obtained by taking the representation of a graphic matroid and adding a small rank matrix to it. And perturbed matroids themselves have close connections to the ongoing Matroid miners project. So, well, I hope at least this version of the problem is now clear. And we don't just study this problem, we go one step further and we want to try and understand whether adding constraints on S, the incidence matrix, allows us to get more interesting results. So in this version of the problem, all you care about is that S is the incidence matrix of an undirected simple graph. But what if I insist that the matrix that I want to recover is the incidence matrix of a forest, or it is the incidence matrix of, I don't know, a chordal graph, and so on. So we formulate the min rank C recovery problem, where C is a graph class, and the only modification now is that I require that the matrix S is the incidence matrix of a graph from the graph class C. C could be any graph class, and I will shortly present our results where we look at a few basic graph classes and study the min rank C recovery problem for these graph classes. Now, is small rank the only good notion of perturbation? Well, definitely not. There are several, and here is another very natural notion of perturbation. Well, you add a small weight matrix. And this gives us a very natural problem, which we call the mean weight recovery problem, where um, you're given pretty much the same input as earlier, but now the question is whether m equals L plus S for some L and L S, where L is a matrix of small having weight, and S is the instance matrix of just an undirected simple graph. Now, in the same spirit as what we saw for min rank recovery, you can also ask this question for specific graph classes by insisting that the incidence matrix is that of a graph in this graph class. And this leads to the min weight C recovery problem. So for min rank C recovery, we were able to show the following. If C, the graph class, is one of these graph classes, either it is just the class of all simple graphs, or if C is a set of all forests, or if C is a set of all trees, connected graphs, and or graphs of arboricity-d. In each of these cases, we actually have a good algorithm for fixed R. So we have an algorithm with running time mn times some constant, mn power some constant times R, where R is the rank of this perturbation that we care about. And for small values, this is actually a polynomial time algorithm. But then a natural question arises whether one can actually get a fully polynomial time algorithm without this exponential dependence on R. Well, it turns out that this is unlikely. There has to be some exponential dependence. Specifically, we show that for these graph classes, the min rank C recovery problem is also NP complete. For the min weight C recovery problem, we were able to show for the same graph classes minus the arboricity-d graphs, one can actually get a polynomial time algorithm. And here the exponent of mn does not depend on R. So in this talk, I will focus on the min rank C recovery problem, and I will sketch our algorithms. So what is the general approach that we are using for our algorithms for these problems? Well, at a high level, it has two steps. In the first step, which is independent of the graph class we care about, what we do is we spend mn to the order r time, and we output a family Q comprising mn to the order r sets. Now, what is each set in this family? Each set is a set of at most r n-dimensional binary vectors. And what is the property of this family? For any possible solution, L plus S equals n, there is at least one set in this family Q, such that if you look at the at most r n-dimensional binary vectors in this set, they actually span the column basis, the column space of this hypothetical L. Now this step is independent of the family C. Now the second step is problem specific, or rather graph class specific. So what we show here is if one is given a column basis for a hypothetical correct answer L, then indeed it is possible to efficiently verify whether uh, an appropriate L and S pair exists. So now let me quickly sketch what step one does. It's essentially a form of brute force. Well, fix this hypothetical L and S uh, that form a solution. It's easier to explain it in this way. Now, look at uh, the columns in some fixed column basis for L. Let the corresponding indices be the set P. And this is something we can guess in M to the order R choices. And what we also know is that since S is an incidence matrix, every column has exactly two ones, which in turn means that if I know M, I know that every column of L differs from the corresponding column of M in exactly two rows. So for these specific at most R columns that I have guessed, the set P, I go ahead and I also guess for each of these columns exactly the two rows where L differs from M. And once uh, this is done, we have essentially just recovered a set of columns of L that form a basis for the column space. So we've actually recovered a submatrix uh, of L that certifies its rank. So now let's talk about step two, which, as I already mentioned, is graph class specific. So suppose that I'm given a basis for the column space of L. Let's call this given set J. I'm going to build an auxiliary bipartite graph H as follows. On one side, we have the column indices 1 to n. On the other side, I have one vertex for every edge in the complete graph on n vertices. Now, how are the edges defined? For every column index n, for every column index x, and for every uh, y on the right side, which, if you remember, is a 0, 1 vector with exactly two ones. So I add an edge between vertices x and y if I can obtain the xth column of M from Y by perturbing it with a vector that is in the span of J. And this completes the description of this bipartite graph. And I claim that now it is necessary and sufficient to check whether there is a matching in this bipartite graph that saturates the left side. So why is this true? Well, if you look at the left side of this bipartite graph, which is the set A here, I have one vertex for every column. And when you think of a matching saturating A, just think of it as follows. What you're doing is you're picking vectors from B and assigning them to the columns in A. And I want this to be a matching because, well, I can't assign two uh, vectors to the same column. And at the same time, since this is a simple graph, I don't want to assign the same vector to two columns. Right? So what I want is actually a matching that saturates A. And it's clear that if I do find the matching saturating A, then it is indeed the case that uh, I can come up with the incidence matrix S and the corresponding uh, perturbation matrix L, which is spanned, whose column space is spanned by J, such that L plus S equals M. Now I'm going to rephrase this claim in a slightly different way, which is going to make it more useful, and it's going to give us a bit more insight into what is going to happen for the other graph classes. So instead of saying that there is a matching saturating A in this graph, I'm going to say that there is an independent set of size M in the transversal matroid that is defined by this bipartite graph with ground set B. Now, what is a transversal matroid? Well, for a bipartite graph H, which sets with sides A and B, uh, let's say that your ground set or universe of this matroid is B. The independent sets in this transversal matroid are precisely those subsets, those vertex subsets, for which there is a matching saturating them. So it's exactly the same thing. Now, this perspective of treating this as a matroid is quite useful. For instance, let's look at step 2 for forests. Now, I'm going to construct H exactly as before. It is the same one, same graph. And M1 is the transversal matroid defined by H with ground set B, what you all just saw. And now I'm going to define a second matroid, M2, which is the graphic matroid or the cycle matroid of Kn, which is the complete graph on n vertices. So the universe of this graphic matroid is a set of all edges of Kn, which are in one-to-one correspondence with the vertices in B, and a set of edges forms an independent set if they induce a forest. Now, what I want is not just that I'm able to actually obtain a matching saturating A. All that will give me is a simple graph. But now I also require that that the vertices chosen from B satisfy an additional constraint, which is that these vertices correspond to edges that form a forest in Kn. And to achieve that, all I need is to say that there is an independent set of size M that is present in both these matroids. So if I have an independent set of size M in matroid M1, clearly it must saturate A since A only has M elements. And on the other hand, if it is an independent set of size M in the matroid M2, then I know that these edges form a forest. So all that's left for me to do is to construct these two matroids, and then um, when I say construct, I mean you either come with a representation or you use an oracle. It's not too important for us. All that's left is to run a matroid intersection algorithm. And if this algorithm outputs yes, then you also output yes. Otherwise, no. So as you can see, treating the simple graph algorithm or viewing it from the perspective of matroids actually helps us quite a bit. And in fact, this theme will continue. So let's consider connected graph. Suppose I insist that S is the incidence matrix of a connected graph. Again, I'm going to construct H, and M1 is the transversal matroid defined by H with universe B. Excuse me. And M2 now is going to be a slightly different matroid. So I'm going to start with a graphic matroid or cycle matroid of Kn, and then I'm going to consider its M elongation. Now, what is the M elongation? The M elongation of a matroid K in general has as its set of bases uh, any M size subset of the universe such that this set contains a basis of the matroid K. So in the case of the graphic matroid of Kn, essentially what you're doing is you're taking a spanning tree and then you're adding m minus n minus 1 uh, additional edges, which could be any such set of edges, and that would be a basis in the M elongation. And this is fairly natural since if you look at any connected graph on M edges, you can break it down into a spanning tree with n minus 1 edges and the remaining edges. So that's what's happening here. And again, once you have the M elongation, uh, it follows that uh, there is a solution L and S where L is spanned by the given J precisely when there is a common independent set of size M in these two matroids. Let's consider arboricity-d graphs now. So what are these graphs? These are graphs whose edge sets can be partitioned into D forests. Now, for arboricity-d graphs, which will generalize our result for forests, we need to do something uh, slightly more involved. But it's not going to be too different. So what are we going to do? We are going to construct H again as before. And now M1 is not going to just define it's not going to be the transversal matroid over B, but it is going to be a gamoid, which is obtained from a directed graph, which in turn is obtained from H as follows. So take H, and I orient all the edges from A to B. And for each vertex in B, I just add a path on D vertices such that the first vertex of this path coincides with the vertex of B. And I'm going to name these vertices v, comma 1, v, comma 2, etc. for each vertex v in B. So this is a directed graph, and given this directed graph, I pick A as a source set, and I pick everything else as the ground set of my matroid, and I define the natural gamoid. So what are the independent sets in this gamoid? Well, these are precisely those vertices uh, which can be saturated with a flow from A. Instead of saying that they can be saturated by a matching, as was the case with transversal matroids, now we can talk about flows. So for instance, the red vertices here, they are independent because here is a set of vertex joint paths from A to the red set. Now notice that if I give you one such independent set, you can move the red vertices along their respective paths and come up with other independent sets. For instance, we can push all of them to the end and that would still be independent. The intuition here is that when I look at the layering into these D layers, every edge of Kn, which has a corresponding vertex here, it has D copies, essentially. And if I pick any of these D vertices uh, into my uh, into my solution, I want to say that that corresponding edge is in my graph or the incidence matrix. But I also want to verify that this is an arboricity-d graph, which means that there is a partition of my edge set into d pieces such that each piece is a forest. And so where the vertex or the chosen vertex appears in the layers essentially tells me which partition it falls into. So that is the general intuition. So this is what M1 is. And M2 is also slightly different. It's now not just the graphic matroid of Kn, but I will take D copies and I'll associate each copy with each layer. If you look at each vertical layer, I look at those vertices and treating them as the ground set, I will define a graphic matroid of Kn. And a direct sum simply means essentially that I take the disjoint union. So an independent set in this direct sum, well, a set is independent if I look at its intersection with uh, each specific graphic matroid and it is independent there. Now we are able to show that with these specific chosen matroids, again, a similar statement holds that you indeed have a solution L plus S precisely when there is a common independent set of size n in these two matroids. So it is sufficient to just check for this. So this is the high level description of all of our algorithms, and all that I really brushed under the rug were just the details of writing down the proof. But I hope you do see the idea and why this would work. And a nice thing about this particular set of algorithms is that they all follow the same pattern, which then also brings up some interesting questions. Well, what other matroids could one be interested in here? What other graph classes could be interested in here, and so on. Just a quick comment about the min weight problem before I wrap up. So there, again, what we essentially do for simple graphs is you can build an auxiliary bipartite graph, which is slightly differently defined, but the spirit is the same. And again, what you will be left with is finding a min weight maximum matching in that bipartite graph. And using that as a starting point, one can come up with the algorithms for connected graphs and for forests. But I will not be covering those in this talk. So to wrap up, this is just the beginning of a very interesting project. So there's a natural set of problems, and as I've shown you, there are some quite interesting combinatorics underlying these questions. Now, with regards to min-rank C recovery, because of this brute force element in our algorithm, it has this running time of mn to the order r, which isn't great, right? But nothing that we know so far precludes the possibility of there being an FPT algorithm for this problem that is parameterized by this rank r. So you might very well have an algorithm with running time 2 to the r times mn or mn square instead of having this terrible runtime of mn to the big O of r. And as I mentioned earlier, it's a very natural quest to try and understand what other graph classes could be interesting here. Are all of them easy, or are all of them hard? Are there natural graph classes for which min-rank C recovery is fully polynomial time? And could we characterize these graph classes? And of course, we've only considered two notions of perturbation. What other notions of perturbation could one consider in this setting?